So before we move on, I will say I work at a center, and we don't always install Julia and Rust. We usually tell the users to do it themselves because we have just one or two asking, and it takes resources to maintain it. But if there's a language out there you really want, advocate for it, and get like 3 different groups you know of to ask us for it, then we will install it, and we'll do our best to optimize it and maintain it.
Yeah, I would say that Python was actually, I mean, it was a community push, right, to support it on HPC, and we had to respond, right?
Yeah, we struggle with Python. You want to make more comments?
No,
Go ahead.
just a very related question. MPI2 is the standard nowadays for internode computing, but is quite old school in some ways. I mean, there is space for a language that could be maybe more high level than this, because in MPI you have to do all the communications yourself.
So I'll make my own comment, and then I'm going to interject here a little bit. I think one of the reasons MPI is so successful is that it is very independent of every other language and mostly independent of architectures. There have been many attempts over the years to have better techniques, frameworks to move data back and forth between nodes, and they have pretty much all just withered away, like the DARPA program languages. And so I think one of the reasons it's successful is because it is sort of basic, hard to use, but it's independent, and it pretty much works everywhere. And when people put effort into making something easier for you, it gets tied to a technology or a compiler or something specific, and it doesn't have as much broad acceptance now. Okay, I had said my say. Go ahead, panel. Anybody want to add anything?
This is a movie that's played before. So what you see, often what you're looking for here with MPI in particular is some higher level abstraction, but we talked about it earlier this week in MPI for Pi. Right, so there was actually easier statements. You're still doing your sends and receives, but you don't have to specify everything. So it's an easier way to develop something like that. Performance can be an issue, and that fundamentally will always be a problem. But that's another example of what I've seen happening for most of my career, is that often you're bringing together multiple languages in order to leverage the strengths of each of them. So I started out as a pure Fortran programmer, right? But in the 90s, when C and C++ were on the rise, what we shifted towards is using C and C++ for program control and memory management and these sorts of things. But when we needed to execute a kernel, we'd call a Fortran routine, right? So this was a different version of assembly. We see this happening again with MPI for Pi, right? And I think that this will happen frequently when there is a feature of one of these languages that it provides value and ease of programming and development, if it can be blended with others that still provide you the performance and other capabilities that it may not be able to provide effectively. Now, the holy grail is that you find something that does all of those things, and I haven't seen any language that does all of them. And for the most part, when they're declared to do all of them, they don't.
They do not. Any more questions?
Thank you.
Okay. How much time do we have left? I'm not even paying attention. Huh? 20 minutes. Okay. Okay, there's a couple of things I want to ask. I want to go back to machine learning a little bit and talk about machine learning in science research. So this is a little bit different HPC topic, but will machine learning replace simulation? Will it replace just a component of simulation? Does everybody here need to get their head around how to set up sort of a simple model? Do they really need to understand it, or can they? We said this about quantum. Now I'm going to say it about machine learning. Can they go forward in their career without knowing a single thing about how this works?
I don't know. That's the
Okay,
answer.
that's a good answer.
And here's why. Both AI, ML, and also this is true of quantum and some of the other newer technologies, they go through this process that the Gartner Group has termed the hype cycle. And so what the hype cycle is it's if you look over time, it's a sort of a growth in popularity, and they reach this peak of hype very early in the technology with early adopters. And what happens is people figure out it doesn't actually work for all the things that they said it would. And so after you've gone through this peak of hype, you go down and a lot of the adoption goes away, and you go through what they refer to as the trough of disillusionment. So I was disillusioned that they would do all the things that it said it would do. And this is true of almost any technology, by the way, and not even just in our space, but more generally. And then what happens is a few of the diehards are still working at it, and they go, but it is actually useful for some things. And so adoption will come back. It'll never get to the peak of the hype, but it comes back, and that's what they call the slope of enlightenment, right? So you've sort of understood, okay, this is what this technology actually is good for, and people will use it for that. AI is being used for lots of things, and in fact, I've seen it incorporated into various applications to take out various parts of the simulation and use an ML model to generate the next time step or whatever else in the simulation. So it's being done today. Will it replace the entire application? Maybe, don't know. In some application domains, particularly the very, very complicated ones, it will do better than most of the simulations because we can't encode the physics sufficiently. And so it's not doing any physics. It's just looking at history and what happened in prior cases like it to anticipate what's happening in the situation presented to it. So it doesn't actually know anything. I guess that's one thing I hope everybody understands about these AI models. They don't know anything.
Right, they're not intelligent.
They're not intelligent. The name is such a misnomer, it's ridiculous. That's why I am happy that terms like machine learning, deep learning, and such are being used more often. AI is still the term that's out there, and it is misleading for that term to be used. So don't think that they actually know anything, because they don't, even though we train them. We're just setting up probabilities in the weights. Will it replace everything? I think probably not in the long run, because the other challenge with these models is they don't have the creativity that's necessary. And so they'll get you close, but they won't necessarily get you where you want to get to.
Any other comments?
Yeah, I would say, and I would agree that it won't replace simulations for sure. It will complement simulations. But I think it cannot be ignored from the perspective of the amount of data we are currently working on. Mm-hmm. So it's a very important tool also to analyze the results and draw some conclusions from the data that we produce by simulations or by using instruments that are out there as well. So one of the examples is the Square Kilometre Array, so the telescope that we are building in Australia. Currently in the precursor projects, they are still looking at some of the data by eye, basically trying to decide whether this specific observation can be useful and whether we can actually store it and then make it available for researchers for further analysis. But it can't be done on the final instrument that they are building. They will have to use some kind of machine learning techniques. Now, the challenge there is that you don't actually have data to use to learn those models, because sometimes you don't know what you're looking for. So there's a lot of research that will need to go in that space as well.
Okay, so do you want to say something? Go.
If you want to move to the next, it's fine.
No, I want you to say something, then I want to make a comment, and then I'll move on.
Okay.
Go ahead.
So I still see space for simulation-based applications, in particular in two cases. So first, when there is no enough data to train models. So when there is no enough source data that you can actually meaningfully get a result based on a machine learning model. And secondly, where you absolutely need reproducibility and being able to understand how the result is produced.
Right.
So both cases, they cannot be substituted by machine learning, and therefore definitely there is a place for simulation in HPC.
Okay, so I agree with all that, but I think though a basic understanding of machine learning is important because it's a very powerful tool. Doesn't mean you're going to use it, but it might be something that you could use. And I do think in a limited form. I do not believe in the whole total simulation. They have to do a lot to convince me that like the digital Earth twin NVIDIA is doing is just going to simulate climate with just data inputs. But it is a very powerful tool, and there are a lot of tools available for you out there for free. You need access to resources, but there are some very nice software tools. Okay, I see you standing.
I just, because it's just
Okay,
last 5
okay,
minutes.
okay, great.
Throw in something from the slide.
Okay, let's do
which is
something.
connecting to this. It's about the dominance of certain tools or hardware aspects. So the question would be, will I still be able to do research if I don't touch AI at all? Right? Similar to this, what about GPUs? Will ultimately all codes need to be rewritten such that they are compatible, also partially running on GPUs? Or will I still be able in 5 or 10 years to run only CPU code, but like highly optimized great ones? So about the total dominance of certain technologies.
Will there be CPUs in our future? Will we build a system that has CPU-only nodes? Or just some, not all, but you know.
Well, and you'll know something about this too, John. Although we talk about GPUs all week, right? The fact of the matter is many academic codes are not running on GPUs still. If you look at the usage of the systems that are available through the Access program in the States, I think still more than half of all delivered normalized cycles are on CPUs, right?
Yes.
Now, that's because it's a workhorse and people know how to use it. Another reason it happens is because many of these researchers are in smaller research teams and they simply don't have the resources to recast their codes for GPUs. So there's sort of a slow adoption problem there. But you know, you're going to see these things for a long time. So while GPUs, the drive towards the GPUs is that's the way you get more performance, because you can't just keep adding CPUs out there. It's the power constraints and other things, and many other things make it too complicated. So I think the other thing is this question that we're asking today versus if we asked it from 10 years from now is probably very different. Because AI is so prominent in the community and it's being used for lots of different things, or at least being explored, likely you should know something about it, right? Now, I think having a basic knowledge of it is important just because it can be very useful for you, and that's useful. But can I get a job if I don't know anything about ML? Yes, but will I have a higher probability of getting a job if I do know something about ML? Yes, right? Because that's being looked for right now. In 10 years, when we understand a lot of things that ML models don't work for and people back out of that, it may not be as important. It will probably be there for the foreseeable future at some level, though. So having knowledge of it will be an advantage to you if you have it.
Go ahead.
I want to slightly disagree. Not really strongly. I think it depends on the profile you have. If you are a computational scientist, I agree then that having the additional skill of machine learning can be very helpful. But from the career perspective, if you are a computer scientist, for example, I fear that already now and in the next years, we will have much more problems to find people having other kinds of skills than those that have machine learning. So skills like operating system, compiler development, so all the infrastructure that is the basic necessity for an HPC system and actually for any computer to run. I fear that we are getting lacking of this kind of knowledge. So if your profile is very strong on these areas and you have never seen a line of code of machine learning, you probably still will have a very good job perspectives, because we will be all fighting for getting you in our computer system. So all these infrastructure, low layers, middleware areas of the software stack, I fear they are getting a bit lost of attention, especially in the education portfolios, which is worrying me, to be honest. So
No,
yeah.
I agree. I know at my institution, my center teaches C++ and used to Fortran, and we just dropped it, MPI and OpenMP, and we do, not because we're faculty, but because the research, the departments quit teaching it, and we had students coming to our center, and they really did not know how to use the codes they were given by their professor that they inherited. And so we started teaching these classes because there's a lack. And you're right, it underlies everything, and no amount of machine learning is going to solve that problem.
So in a sense, what I'm saying is when everybody else is doing that, if you have a profile that focuses on something that is starting to be lacking in the community, you are getting yourself in a unique position.
Yes, I agree totally.
So I don't want to disagree with you entirely. However, I will state that I know of projects that are going on in data centers that are using AI models to control power and cooling controls for systems using an AI model. There are those that looking at scheduling systems using AI models to optimize scheduling. So it creeps into lots of different things. Now, we don't know that those will be successful, right? But even when you're on the infrastructure side of things, AI models, at least the use of them, maybe not the development of them, but the use of them is probably important.
In this one, I agree, yeah. So I was speaking more about the more lower, so middleware operating systems, so really the near metal stuff. But in scheduling, I fully agree with you, and monitoring and so on.
Go ahead, Dennis, you picked it up.
Yes, I want to add one more, say, application example. That was for the original question, will GPUs be replaced by CPUs be replaced by GPUs? So like the example so we have programmed a quantum computing simulator, which is 20 years old. It runs in Fortran still. And it has obtained several world records. So it's the largest universal quantum computer simulation. That's sort of the main application that we use this for. And we did also port this thing to GPUs because we saw GPUs are on the rise. And we also felt like, okay, you have to do GPUs. And this is the but. So the recent world record from 2019 that we did on the K computer here, the predecessor of Fugaku, we would still have been able to achieve all these things without the GPU code. Okay, on the K computer there were no GPUs, but we're doing it on a current GPU cluster. So the thing that I want to get across is the GPUs did make it a little bit faster, but if we had not ported the code to GPUs, we would still have been able to get the same simulation done in a little bit longer time.
Okay, how much time is left? I want to do one.
8 minutes, and if you want, I'll just shoot out the last topic questions. Or do you want to continue?
I think I want to ask there are a couple questions on there I wanted to get to, and I'll poll the audience. One was about power concerns in the future of HPC and how to support it with the amount of power it's drawing. The other one was, do we really have a need for an exascale computer to run an application? Is there an application that has to run at X scale? Which one do you want to do? Power or exascale application? Exascale application, anybody? Power. Looks about the same. Let's try to do both. We're going to do 4 minutes on exascale application. Go. Do we really need an exascale computer to run an application, or should we spend those resources on more petascale, small exascale systems?
There's an economic problem with that because there's a shrinking number of applications that really need that kind of platform to run on, that kind of capability. Weather and climate prediction is one of them.
A big one.
So there will be a shrinking number of really important applications that exist. And so at some point, there'll be a business and political decision that has to be made about, are we going to build yet a larger one for a smaller number of applications? And it'll be based on what is the benefit that's derived from that. And we don't know how that equation balances out right now.
Any more comments?
Well, not much to be added. I agree with this. It's a conflicting target that we have at some point. So we have the problem of how many users are we actually serving with this huge system?
Right.
How much energy does this need?
Right.
And which problems do we actually need absolutely to solve, and we need this machine to solve them. So it's a difficult question. On the other hand, I think the same kind of question was posed before exascale and probably before petascale. So you are longer there, you probably can have a bit more time perspective on that.
And the problems seemed to emerge as soon as the computer emerged, and it was always busy. Okay, so I'll switch to the power question. These systems rate megawatts of power, right? I think Argonne now has 60 megawatts or 80 megawatts of power. I don't know how much Jülich has, but they're very power hungry, very power dense. This sort of plays into the whole exascale. Is this needed? Do I need to put a nuclear power plant right next to the center for the next generation? Do I need some sort of super cooling because the power density rate has gotten so high for the GPUs? And at your centers, are you trying to plan for this? I assume you are planning for power efficiency. And do you have some concept of renewables to power your center?
Yes to all of them. So, first of all, I think the original question is, will energy consumption put constraints on HPC centers? Definitely, it does. It does already. And is the pure use of energy, and is also the cost of energy. So at least in Germany, 2 years ago, with the situation in Ukraine and the energy supply into Germany, it has been a dramatic rise on costs that in some centers it just led to shutting down part of the resources because it was not possible to run all of them at the same time. So we definitely are doing a lot of work on improving the energy efficiency from the infrastructure up to the application side. So infrastructure, you spoke about it, cooling techniques, reusage of the heat that we produce to heat the buildings around it. And on the scheduling side, we are also looking in trying to maximize the use of the machine. So it has to be running, it consumes a lot of energy. Let's get the most science out of it at the time it is running. So we are looking into things like co-scheduling applications, something we did not do ever in the past, and we always try to get away from. But I'm not sure it will be a long-term possible to get out of it. So maximizing the use of the machine, reutilizing the energy as much as possible, driving from renewable energy sources as much as we can. All of these questions are definitely on the top of our table, very high in the priority list.
Anybody? Okay. I'd like to know if there are any comments from the audience about either of these last two topics. Go ahead. Can you go to a microphone? Thanks.
With the power efficiency stuff, we see a lot about minimizing CPU and GPU power. Do you see any trends in minimizing the amount of power RAM consumes? Because I understand that's also a big part of it.
So, trends to minimize the power for the computing, is that what you asked?
Trends to minimize specifically for RAM, because we see a lot of making CPUs and GPUs more efficient, but...
to make memory more efficient. So, technologies to make memory more efficient.
Well, not necessarily making it more efficient. Some people in the research, this is all research, so it's not really production ready yet, but they are looking into memory disaggregation, for example. So you reduce the volume of memory inside of the node, and you have at rack level or somewhere pools of memory that you can allocate from the whole system. So at least you reduce the amount of total memory you put on the system, and therefore the energy consumption. But
yeah, and I guess just a push in both from the software but also hardware side to minimize the moving of data between different memory available on devices. So I think this is definitely something that people are looking at. But I also wanted to make a comment to the previous question that. So our system is based on GPUs, and the main driver in that was really energy efficiency. So of course the speed that you can achieve, but energy efficiency within the constraints that we had defined this specific architecture that we were able to provide to researchers. So at this point of time, it cannot be really ignored, right? But how it will look in the future, the situation might change, and we might need to adapt to a different hardware architectures. We've seen that in the past, and I think this is part of the business.
Well, so this is one of the things that has driven the adoption of GPUs, especially at computing centers. They're so much more efficient when you look at flops per watt. Now, that's just one measure. When you look at actual peak percentage of peak performance, say, of your application on a GPU versus a CPU, it takes a little more work to move it up on the GPU than it does on the CPU. And so when you look at these power numbers and you have applications in mind, you should really look at the application performance in flops per watt, not just the peak performance. But the GPUs are, at peak performance, much, much more power efficient than the CPUs. Go ahead.
Talking about CPUs and GPUs, also on the CPU side, right? We have seen a market increase in the number of cores per node, right? And the number of maybe the memory per core is probably proportionally dropping, or at least not increasing, right? So do you see with the unified memory architectures that slowly even the hardware, we have this COCOS and all the portability stuff, but also the hardware itself might start to converge into, if in a few years you have a node with 1,000 cores, I guess you have to program it in a very similar way than you have to program a GPU for it to be performant, or maybe not.
So I think you're asking, is the hardware converging? And I think it is. Do you want to comment, or you want me to say something? Okay. So what I would say is it most definitely is. Two of the technologies John sort of didn't mention, but indirectly mentioned, Grace Hopper and AMD's MI300A are a combination of CPU and GPU, and they're more tightly bound, and they're more power efficient. It'll make it easier to program. My biggest concern with these technologies is there are new bottlenecks between the memory on the different devices, and it's still unclear how that will work out. But basically bringing the extra device, be it the GPU or a quantum something, closer to the CPU is the sort of the end game, and I think where everything will go once it's proven that it's definitely needed. And they're gonna, like, GPUs are gonna stick around, so we still need a CPU to drive them. So we got to get it closer to the CPU to maximize the data bandwidth and minimize the latency and greatly reduce the power needed to move the data back and forth. And that's what these new systems will do. Can you go to a microphone, please?
Yeah, so a lot of people coming from statistical background, predominantly programming R, but it looks like throughout this summer school, it sounds to me like R has been sidelined. So I want to ask, is R out of the game when it comes to HPC? Or
does anybody want to comment? R is a statistical programming language.
Yes, so R is probably in competition with Python, right? So many things that R could do quite well, you can nowadays do if you use the right NumPy or the right NumPy function call or the right extra package and so on. I think R is still used by certain communities who, in the same spirit as while we are still using the Fortran code, they have started to, I think the finance communities, they have started to incorporate it into their code, so it's legacy code now, and I think in these applications there's also no drive to do everything again from scratch in another language, so R will stay there, I think. But I don't think that R, because when it came out, when it became popular, it was supposed to replace every kind of statistical analysis language. But this has not happened, and I don't think it's going to happen in the future.
And I think it's a great example of the problem with R is and why you see these things showing up in Python as modules you can bring in, is R didn't provide an easy transition path.
Right.
And that's been the hurdle that we've been able to get over.
Okay, so we're about to end, but I'll make one quick comment about R. So we have a lot of R users on our system, and one of the biggest issues is it's hard to scale R out and get performance, but not as hard with Python. And so if you want to perform better, you should probably look at how your R translates to Python. I'm not saying R is not useful. I'm just saying it's harder for our users to get good performance out of it. And I've been told we're out of time. So I'd like us all to thank our panel. And if you have any questions on the future of HPC, you can ask any of us or anybody here. I mean, and you have your own opinions too, so feel free to share them. Thanks.
There may be a last comment I would like to add is just to stress that you are actually the future of HPC. So we were really very interested on seeing your point of view, on hearing what are your ideas on the topics we just discussed.
Yes, that's right, because you will be guiding this. Okay, what's next?